Hello, my name is Timothy Faerber. I am a graduate student in the Physics and Astronomy department, and here is my 3-minute thesis presentation. My research so far has been focused on the interstellar medium, which is the gas and dust that fills galaxies in between the stars. And it's important for astronomers to understand this gas and dust because it can help us to understand how galaxies form and evolve and how new stars form. For this work, we decided to study a set of 35 H II regions, and for our non-astronomy audience, H II regions are just regions of gas and dust surrounding massive stars. The goal of this research was to study the photodissociation regions right at the edge of these H II regions, which is a thin shell where you can actually detect expansion and kinematic signatures in the H II region. For this work, we used archival C2 or ionized carbon emission data from SOFIA, which is a now decommissioned observatory, and we wanted to look for signs of expansion in these H II regions along their outer edges and rims where we can see this C2 emission. We wanted to look for expansion here because there's a long-held theory that as the energy from these central single star or stars pushes out on the inner boundaries of these H II regions, they will expand outward into the surrounding gas and dust, and they'll knock that gas and dust out of its equilibrium, which can lead to the formation of new stars and kind of triggered star formation along a chain. To do this, we construct what are called position velocity diagrams. We can see one of these in the left figure of the PowerPoint, which is taken from the red axis in the right figure of the PowerPoint, which is what's referred to as a moment zero map, or essentially just a map of all of the ionized carbon emission in that H II region. And back in the left panel, the x-axis corresponds to the offset along the red axis in the right panel from bottom to top, while the y-axis shows us the velocity space. So if we had a perfectly uniformly expanding sphere, we would expect to see a perfect circle centered around the rest velocity. For this specific H II region named N17, we have a rest velocity of 20 kilometers per second with an offset of negative 17 kilometers per second, meaning a blue-shifted expansion towards us of 17 kilometers per second, with no red-shifted expansion present. And this is a common trend across the sample. Out of 35 regions, we find 12 that show signs of expansion with an average velocity of around 12 kilometers per second. Of these 12, 8 show only blue-shifted expansion, while 1 shows only red-shifted expansion, and 3 show both blue-shifted and red-shifted expansion. Next, we compared our observed expansion velocities to theoretical expansion velocities from both stellar wind and thermal heating, which are the two main ways that an H II region can expand in theory. We find that both methods of expansion are present in our sample. We believe the overabundance of blue-shifted expansion could be due to a selection bias where the regions expanding toward us are the brightest, but don't rule out a small sample. In the end, we show that H II region expansion does occur due to some form of stellar feedback.